MongoDB is a document-based NoSQL database. It became very, very popular for its schemaless way of storing documents, because the friction when it comes to writing code has gone compared to SQL-based databases. But I get this question a lot, and I thought this video will be the perfect segue to actually answer that question. What is really the difference between NoSQL and SQL? So I'm going to address that in this video. But the main purpose of this video is actually going through the evolution of MongoDB internal architecture. So this is a topic that very rarely people discuss because we're going into the bowels of the database, not the front end in a sense that how you interact with it and store data, right? So we're talking about the actual architecture of the internals, right? There's been evolution up until version 5.3. A very interesting feature was added. It's called the clustered collections. So I'll go through this, the evolution of this. So I'll discuss what is the difference between SQL and NoSQL, and in a very deep way. And we'll discuss the first version of MongoDB, where it starts with their storage engine, mmap v1, then the WiredTiger, acquiring them back in 2014, I think, and then moving all the way to the recent changes, which is the clustered collections. And this is all going to make sense by the end of the video, hopefully. How about we get started? All right, so I'm going to use my Medium article, at least the images in my Medium article, to illustrate this. Think of it as like as this slide shows, but go ahead and make sure to follow me on Medium. I started posting a lot of content there. If you like more the written Medium than actual videos. But the first thing we're going to discuss is like the database internals. If you look really at any database almost always will have two pieces. And the most piece that we actually deal with and interact with is actually the front end piece of the database, which is the API. You see, the most popular databases API to actually communicate to the database, to tell it what to fetch, to actually ask it to store something, is the SQL language, which stands for Structured Query Language, right? And that is the API that we know and love. And another piece of another different API could be like Redis or Mongo, right? So, hey, get this document and store this document. There is no structured query language. There is no selecting tables and fields, right? It's just its own different API. So the API can actually change based on the database. The second portion is actually the data format. When I ask you to get something or I want to store something, what am I giving you and what am I taking back from you? And this is where really a database can shine. It's the core of any database system, the data format. So for the longest time, databases has always been tables and rows and columns, right? And to interact with these rows and columns, you use the SQL language, right, to query it. So when people designed the database back in the 70s or 60s even, right, they thought about it always as, hey, it's always going to be tables and always going to be rows and always going to be columns, and then the application can build on top of it, right? We built it bottom up, if you will. And then so that's one data format, right? But then people challenged this. People came in the 2000 era and says, wait a minute, why do I have to be really fixed to these tables? My application has nothing to do with tables. Right? As the web evolved, as the evolution of the web, right, came in, and JSON and documents. Really, I want to deal with documents. I don't even have a schema per se. I don't have tables with a specific schema. I want to be flexible. Why are you forcing me to do tables? And that's the idea of where documents came in, later graphs came in, later other column-based storage came in, right? Instead of row storage. All of this, it really automatically the database became these two parts, where the front end and the storage engine, which is the most important part, the storage engine here. You see? So the storage, once we discuss this, there's the data format, how I'm returning these things to the user, and the user here, I really mean the application. And again, the front end here, I'm talking about the actual database front end. It's in the database, right? Portion. And then the second portion, which is the most important part, is how am I storing the data on disk, right? And the storage engine doesn't really care what you're storing in it. To the storage engine, you have something called a page. And in the page, you have bytes. That's all what it cares about. And the front end part of the database will say, hey, by the way, in this page, there's a bunch of rows, right? I have a row store, right? Where I have a table and I put the row and all the columns. And then right after the final column of the first row, I put the second row. And you can see that it's just if you think of it like an actual page, a rectangle, the first row, and then followed by the second row, followed by the third row and all its column, fourth row and all its column, fifth row and all its column, until the page fills. That's why the storage engine has a property called the page size. In AnoDB MySQL, that's 16 kilobyte. In MongoDB, I don't remember MongoDB, but Postgres is 8K, and you can change this page size. So in Mongo, what we're storing is just a document. It's a JSON document that the front end receives, and it turns it into a bunch of bytes, and then we flush it to a page. And it's the same thing. The document, key, the first key, and then the value, and then we just write it to the storage engine. So if you think really, really about it, it's always the storage, what you're storing, and how the front end is actually extracting this information. So document, graph, right, based database. When I say, hey, this is a graph-based database, the storage engine doesn't care. It's just how the front end part of the database actually organizes the bytes such that when I store them, I want to read that page and get as much efficiency in my read as possible. So another piece of the storage engine is indexes, right? Because now we're storing things in a bunch of pages, right? How are we storing them is also another story, right? Are they just a bunch of files? Does each file represent a table or a collection in MongoDB, right? Or am I storing the actual data in the indexes itself? We're going to talk about all that, right? Indexes will help fast track what you're looking for, right? That's also part of the storage engine. The type of indexes you're creating. Is it a gist? Is it a B tree? Right? And all really helps pinpoint exactly what page you are trying to read. Right? So if you have a table or a MongoDB collection, these MongoDB collections just a bunch of JSON documents, right? Storage engine can decide, you know what, this document is really large. I'm going to decide to compress it. So that's all property of the storage engine. The front end doesn't even know that this document is compressed. All it does is, hey, just give me that document. And this part will just decompress it and give it back to the front end, and the front end will return it, right? So there is like a clear separation between these two. And they can share tasks as well, of course. The data files, like where is the actual full data? You know, because indexes only have part of the data, right? It's like I'm indexing on the first name, and give me all. First name is a bad index. I don't know, salary maybe, right? Salary is another data structure we create, and then we traverse it back to get back to exactly to that data, right? To that data file, which then pulls the entire document or row, and then we return it. And you can really be creative here, and that's what people did, right? The storage engine was also responsible for transactions. You know, when I'm changing this and this and this and this and this, I wanted to do it as one unit of work, such that if there is a failure, please roll back all these changes. Don't persist anything halfway through. I want to be consistent. I want to be atomic. And I want to be isolated, my concurrent transaction. All of these are properties of the storage engine, really, right? I want durability. I want that if I say commit and you told me the front end, right? That's another thing, right? The transaction will say, hey, I want you to commit. And the storage engine will say, yes, you committed successfully. If I get the success and return to the user, and then later you crashed, that data better be there when I come back, because you told me you committed successfully, right? All of these things, WAL, the write-ahead log, or journaling as MongoDB calls it, right? As I'm writing things, usually when you write things, it needs to go to the data file. That's where the major storage lives. But then writing to the data file is really expensive, because you're writing in pages, these massive pages, 8K and 16K. So imagine like you're touching one column, one property, you need to write a whole page. There is no writing 1 byte in databases. No, sir. We don't go to disk and say, hey, just change that tiny byte, or just change that tiny 3 byte, or just change that 1K byte. Nope, you can't do that. That's not how SSDs and hard drive works. You have to write in chunks, in big chunks, for efficiency. You do an IO, you're going to write an whole sector. You do an SSD, you're going to write a whole page, or a block, or a erasable unit, based on the new technology of SSDs, right? That's where shingled hard drives comes into the picture, where they increase the write portions and stuff like that, right? We don't have byte addressability on disk, unfortunately, until today, 2022. We have byte addressability on RAM. You can definitely write single byte in RAM. Definitely, that's fine, right? But on disk, persisted, no, you gotta write in pages, right? And that's what we have today. And because of that cost, right, writing to whole data files, what the data storage engine does, like as you change, all these changes goes to RAM. We call them dirty pages. The moment you touch a page where you have a row or collection or document, we just mark it as dirty. And again, the storage engine doesn't know it's a document. It just knows it's bytes. It knows it's a page with a bunch of bytes that you touched, right? And then you write in memory, and so it's fast. And then later, the storage engine will collect as much changes as possible and then flush it once, right, to the database. All of this is the job of the storage engine. Right? I still didn't come to the difference between SQL and NoSQL, but you will get there. Right? You're clearly gonna see it. I think by this time, if you're still watching or listening, you're probably gonna know the difference, right? So we're not writing immediately, right? We're collecting these changes. You might say, Hussein, but wait a minute, you're writing to RAM? If I commit, you're writing to RAM? What if I crash? That's the problem, right? So that's why, in case to recover from the crash, we create this thing called WAL, the write-ahead log. So as we write to the RAM, to these data pages, we also write on disk tiny things that says, hey, here's a journal. On this date, right? Dear diary, on this date, I updated the salary from 10,000 to 10,050 cents. It's a bad year. What do you want me to say? Right? So, and this, on this date, I wrote this. On this date, you just write the changes. So that in case of a crash, we're going to lose the dirty pages on memory. But if I came back, I have all the WAL, and I have the last checkpoint on the data file. So I restore that, and I redo the changes. I apply the wall to the data files, and now in memory, I have the final representation as it was when I crashed. Brilliant design, right? Anyway, I'm going all over the place, but the storage engine front end, that is the main pieces. So we talked about what a front end is. We talked about what a storage engine is. The difference between the SQL and NoSQL mainly is this puppy, the front end. The NoSQL guys came in and says, you really restricted me with this tables and columns and this SQL. I hate SQL. I don't like SQL at all, right? I don't like it. And it just doesn't fit our application. I want just to give you a document, just store it. And that's where they redesigned. I think someone came up in one day and shop was like, no SQL. They started a movement. They said, no SQL, no SQL, no SQL, no more SQL. And they created their own technical storage engine. And I believe, if I'm not mistaken, they didn't even have indexes. So you guys are so, because when databases, Oracle and SQL Server created, they were just so wired to be, to have tables and rows. And so everything was glued together and sticky. Can't change it. So they created everything from scratch. A storage engine. I'm storing just documents, for example. That's the first use case. I have a document, a JSON document, just store it. It's just a bunch of bytes. Later, they added transactions. Later, they added wall. Later, they have the indexes. They slowly added it. And then the API, just a get and set. The user will get a document, and we're going to store it on the storage engine. That's it. It's just a bunch of bytes. We're going to convert the JSON into bison, binary JSON. And then we persist it. That's the only difference. That's the only difference in SQL and NoSQL, right? The data format, which we changed it from tables and rows into documents, and then the API, which is the get and set instead of just SQL. And clear separation. And then, of course, there are out-of-the-box storage engines, such as LevelDB or MyRox, right? RocksDB, sorry. RocksDB is a very popular storage engine that does exactly that. It takes a bunch of bytes, doesn't care what you have in your bytes. It doesn't care. It gives you the beauty of indexes and storage engine and all this stuff, right? But then in the front end, you can build your database the way you want. That's why you can build a graph database. So graph will prioritize not rows or columns per se, or even documents, but the traversability. Like, so if this node connected to this node, connected to this node, I want to store them next to each other, right? In this way. And so that the whole goal between the API and the storage end and the front end is that when I do an IO and I give me a page, you want as much as possible that page to have everything you need. You don't want to go back to read more pages. And I can go for ages about this, this just the efficiency of the AI. I think this is the most important thing. But we still didn't get to the main part, which is the MongoDB databases. So now we talked about NoSQL versus SQL. What's the difference, right? Now, what we want to discuss is the first version-ish of MongoDB. This is prior to 4.2. MongoDB first storage engine was called Memory Map version 1, which is literally just a bunch of data files, right? And the data file, right? The data file are stored document after one document after the other. Now, I don't know if there is one data file have per collection. Maybe when you have a collection, you'll have a data file. Maybe it's different. But what's the brilliant design behind the first version was an offset based. That means, hey, I want this document, right? This particular document with an ID. So what Mongo has is a unique identifier, right? If you know about that, and your unique identifier will tell you exactly about this document, right? And there's an index attached to it, right? And this index, this is a B3 index. When you traverse the B3 index, you find the IDs. Like, okay, it's in this page, and then you find it. The pointer of this unique identifier is something called the disk location. I think it's a 32 byte. It's actually 64 bit, sorry. It's a 64 bit pointer, 32. The 32 bits, the first 32 bits tells you the file name, which file, and the second 32 bit tells you the offset, right? Because now you know which file, but then the file is 1 gig, right? Where exactly is the document in this file is the offset. So with one single read, you can go exactly, because this is how the OS read, right? The OS read will give you the file name, says, hey, go exactly to that location. You can absolutely do that, and the file system allow it. To say, read that portion and read for X amount of bytes, right? So I suppose another property is the document size. So you need to store also the document size, right? So it says, hey, read this part. And then you're going to read that, right? And then you get a bunch of pages probably. And then if you're lucky, you're going to get one document or more, right? That's why the document also have a fixed size. You can't go beyond certain size because of these limitations, right? So now you got it. So you do one B-tree scan from the ID, right, to find exactly which document to pull, right? Again, you're going to get a bunch of bytes, and then the front end is responsible to parse the bytes to actually find documents per se, right? And of course, if this was like a relational database, then going to be columns and rows, right? If it was a graph, you're going to parse it such that you know the beginning and the end, right? And it's not really rocket science at the end of it. So we're getting a big O of log n, right? So it's just a one IO or multiple IOs to traverse the nodes. That's why it's important that the B tree is small enough to fit in memory, such that because the index is just not a data structure which is persisted on disk. You read it from disk and you put it in memory. Hopefully it fits in memory. That's why Discord actually, one problem that Discord faced was they moved from MongoDB because their indexes were so large they couldn't even fit in memory. And if your index doesn't fit in memory, that means as you traverse, right, the operating system will do the paging and swap files, and will swap things to disk if it's not used, right? And this scanning is going to become slower just to find the disk log. Okay? But that was the original thing. The clear problem with this is anything you touch, you change the document size, you updated it to a longer string, the entire file is now scrambled, right? Because the offset, you change the physical offset of the disk, right? I suppose you can play with games with this, but this became very, very problematic, right? Because the documents are based on offset. The moment you change the document size, you push it a little bit, the whole offsets are now off, right? That was the original design, I suppose, if I'm not mistaken, in MyISAM in MySQL, which is no longer used because of the same reason. Yeah, it's nice. For read only, it's beautiful, right? If I'm not changing it, yeah, it's just very fast. You know exactly what it is and you pull it. But as you change it, it becomes really a mess. I suppose you can play tricks. Of course, you can update the offsets, right? You can update the offsets, but that was a problem. Plus, another problem with the mmap is the locking model, right? That's another thing that's the responsibility of the storage engine, really, locking, right? How do you prevent two people from editing the same document at the same time? You shouldn't really do that, right? Databases, no two databases will allow you to update the same unit of work, if you will. If it's a row, if it's a table, if it's a collection, right? In mmap, it was very strict, right? Imagine this, like the first version of mmap was they didn't bother. Imagine, because these are people who are rebuilding a database from scratch. So they didn't think about all this stuff that the databases people have been doing it for years, right? For decades, actually. So the first problem they run into is like, Two people can change the different documents. Oh, the offsets are out of base. You know what? Let's just create a lock, a global lock. So the first version was a global lock per database. So no two transactions can actually change documents in different collections at all. So if you have collection 1, collection 2, you can even change collection 1 and collection 2 documents concurrently. They are serialized. There is one global lock. Again, that was the first version, because it's a single database lock. She says, hey, read these data files. This tells me that the data files are actually collapsed. So multiple data files, multiple collections can live in the same data files. That's one reason. Right? You have to acquire a lock so that no two transaction can change it. But then they improved this in in the version 3s. That wasn't the version 2s of Mongo. In version 2, they made it a collection level lock, which is still not good, right? It's for the SQL people. It's like saying a table lock. Imagine you have a table of 1,000,000 row, and you want to insert a row in the table, and then you want to update another row in the same table. Has nothing to do with each other, right? Imagine these are blocked. Yes, it was blocked. And if you're using a map, this is still the case. One collection, which is deprecated, by the way, v1 is deprecated. Now, one collection is a per collection lock. So now, sure, you can do a concurrent write on two different collections, right, without blocking. But now, if you're updating the same document, that's a problem, right? So then it became very challenging to manage this storage engine. So what MongoDB did is, as you know what, let's just acquire this WireTiger storage engine. Very, very popular, very efficient storage engine. So what they did is MongoDB just scrapped this, and they bought a storage engine out of the box. This has become what we call WireTiger, right? And the front end didn't change. So your application code doesn't change. The storage engine in the backend changed, right? So now this is WireTiger. They gave WireTiger the ability. Here's the thing. With WireTiger, the ability of document level locking has become popular. Now you can update two documents on the same collection. I'm now saying these things, and you might say, it's like, this is all exist. I know, but I'm telling you the history of things, because building databases is not really a trivial thing. The brilliant engineers went through this, and they run into a lot of challenges, and this is one of them. So the WireTiger storage engine allowed you to update two different documents on the same collection concurrently, which is now a beautiful thing, right? Now we can, and this has now made it equivalent to basically all databases, because the databases have row level locks, like at least MySQL and Postgres. You can definitely update two rows on the same table, but you cannot update the same row on the same table, right? We acquire a lock, and then the second transaction tries to update the same row, that will basically pause the second transaction, right? With row level locking. Now there is what's that database called? Yoga DB, if I'm not mistaken. They even introduced column level locking, which is another thing. Like if I have a row and I'm updating field 1 in the row, but you're updating field 2, technically we're not changing the same thing. Postgres will lock you even if you're updating different thing. MySQL, if I'm not mistaken, they will also lock you because it's a row level lock. But now you can also include column level locking, which says, hey, if you touched this row but different field from this row. Same thing with the document, right? I am really just updating this field in the document, in JSON document, and someone is inserting a new field or updating another. Are we locking? Do we really need to lock it? Well, at the end of the day, this is what we do. We lock it. So yeah, if you happen to have two transactions updated in the same row, even different columns, you can't do that unless you have column level locking, right? Or key level locking, if you will, in Mongo, which I don't think it exists. And believe me, when I'm talking about these things, this is not cheap, right? The moment you introduce column level locking, that's another expense, because now you have to keep track of what you're locking. And locks are, guess what, in memory. And raw locks are more expensive than page locks or table locks or collection locks, because you just need one. Versus if you have million and you updated a million rows and transactions are in progress, that's a million lock, right? Imagine adding column locks to that. So million times whatever columns you're updating. It becomes really challenges, right? Yeah, building database is not trivial. All right, go back to WireTiger. We talked about that. Right, Mongo WireTiger introduced compression, which didn't exist, by the way, in MMVB, right? It didn't exist here. WireTiger introduced compression. Now, when you actually take the document, WireTiger compresses the JSON document. So that's really brilliant. Now because especially JSON documents have these fields repeated all the time, right? The field repeats. So you need to compress it. So MongoDB WireTiger actually compresses that so that's tiny. Why is it tiny? Because now if I'm compressing it, the page will fit more document. One IO will give me more documents than it was a one IO in uncompressed. If one IO uncompressed give me 3 documents, one IO compressed in a single page will give me 20 documents. This is really powerful because now I don't really need to go, if I'm fetching 20 documents in the older models, I have to do multiple IOs. I have to hit the disk multiple times versus in the WireTiger, just one, pulled all this stuff, compressed, do a little decompression in the client side in memory, and you get a beautiful 20 documents. The major thing you have to think about here, how do I save IOs? That is the number one job of a DBA, of a developer, of a database. Saving IOs. The less the IO, the faster the database. Nothing else matters. That is exactly what it is. All right. So now, the way WireTiger store the database is completely changed. It's no longer using this disk lock thing, right? Where it's just a bunch of data file and then you have offset, because offsets are really terrible, right? For changing, like the offset changes and you have to update everything. Like changing one document will screw all your offsets, right? So what they did instead, they stored it as a cluster B3 index. And I talked about this in another video, but I'm not going to go in details. But in a nutshell, right? They have something called the record ID here. And you can basically create anything. This is a hidden index, cluster index in WireTiger. And based on the key, you can search. And when you get here, the value is actually the entire document. And not only a document, right? But physically, all the documents, right, are ordered next to each other. So the page that you land on here in the leaf pages are the data. Is the data. This is the data. The entire data is the index. That's what a cluster index says. It's by default what you get for MySQL, not in Postgres, but in MySQL, everything is a cluster index. Every table has a cluster index, and that's how your data is organized around the index. So your table is organized around this index where the leaf pages is the data. So now if you land here, you get the document, and guess what? Because it's on the one page, you get any document before it and you get any documents after it. And because it's compressed, you're going to get a lot of tight documents as well. So you read this page and you get all the documents nearby because it's ordered. Not only that, each leaf page in B+3 is actually linked to the next page and to the next page and to the next page. It's a linked list of pages. So the entire data is right here. So if you find this, if you want to do a range query, it says, find me all record IDs between X and Y. And we're going to talk about what record ID is, because this is not the ID of the document. And that's the problem that WireTiger and Mongo introduced in a way. Now, if we have this, you do if you do a range scan, you're gonna get all the documents that are next to each other. So a range scan is really powerful in B+3, especially if it's clustered, because now you're gonna get all the nice documents tucked in together, right? So you can find your document using a B+3 search in WiredTarget using the record ID. But guess what? What is this record ID? It doesn't mean anything to the user. This is an internal thing. But where did this disk lock happen? This used to be called the disk lock, but they changed it. And that's what they had. They had this as disk lock, and their indexes, the ID, the actual user-facing ID document index, has been mapped always to the disk lock, because that's what we had, right? Disk lock. That's exactly this. This is this. This used to be this disk lock. They later changed it to record ID. So it's like, it doesn't make sense to call it disk lock. But then this record ID now is just a pointer to where? Not to disk. It is a pointer to this B+3, which is the hidden index. So now if you're actually searching for the ID, the primary key, you're doing 2 lookups in WiredTarget, not 1. So actually, ID lookup in WiredTarget were slower than the older one, because now you have to search 2 indexes, you have to load 2 indexes in memory, double the space, double the searches, double the IO. You have to write to the multiple indexes because you have to sync those 2 guys together. Secondary indexes, not so much, because the secondary indexes, right? If you think about it, really, secondary indexes now just point directly to the record ID. So yeah, in this particular case, all of these indexes always point to the record ID, whether it's a primary index or a secondary index. They all point to the primary key. Okay? And that's what's causing us the double search effectively, right? So very similar to MySQL, not quite, because MySQL primary key is actually this thing, right? But the primary key in the first version, at least from 4.2 to 5.2, very recent this change, by the way, right? Until very recently, 5.2. 4.2 to 5.2 is like this, where you search for ID, you find this, and then you do another search, another B3 search. This is not a big O of 1, right? This is a big O of login plus big O of login, 2 searches, right? Whereas this guy, you do big O of login and then big O of 1. Boop. So now we have this beautiful design. The problems we understood. Now the ID is a problem. We have to kind of a duplicate style, right? The record ID is a 64 bits, same thing here, but secondary indexes all point to the record ID. That's the state of art as of 5.2, right? And the ID index is just another secondary index at this point. It's not really a true primary index, right? Because the primary index, by definition at least, is the clustered index, right? It is this one, but we have now double. Now let's go to the final stage where 5.3, I think, is July of 2022, really. Very, very brand new feature. It's called clustered collections, where you can create a collection and you can make it a clustered collection. That means the WiredTarget hidden key disappears. Right? And instead, this becomes your hidden index, effectively. This becomes your clustered index. And the ID field is the main focus for this. Now, if you're searching by ID, right, you will immediately search by ID, do a little bit of lookup, and then find the document, because the clustered document is right here. All the leaf pages have your full documents right here. Pretty neat. You don't really need to do these 2 lookups anymore if you're searching for ID. Right? Again, this is an option. It's not, you don't have to do it, right? So if you still want this design for some reason, we're going to talk about why in a minute. You can still have it. But now, in this guy, you can do this. What's the problem with this now? We talked about the good thing. The good thing, single search if you're using the ID or MongoDB, right? If you're looking up a document by its ID, it's a single beautiful search. Immediately find the document, base and document, right? And if you're lucky, you're gonna find anything in next to it, right? It's not just one document. This is a collection of documents in a single page. I gotta find out what's the page size in WireTiger, right? But this is what you get. You're gonna get this, and it's gonna be cached in memory temporarily, right? So if you're lucky, the previous ID next to it is also, you're gonna get that as well, right? If the sequence really makes sense here. The problem, my friends, is now let's go back to secondary indexes. The moment you introduce it, now this becomes identical to MySQL. MongoDB after 5.3, if you choose to be a cluster connection, it's almost identical to MySQL now. It becomes identical to MySQL. The ID field, which is the primary key, is the cluster index. The secondary indexes point to what now? They have to point to the ID, right? There is no record ID. You moved where the data is, right? Previously, the secondary index, and I should have drawn this, but sorry, I did not. The secondary indexes used to point to this thing, the hidden, which is a very tiny value, record ID, 64-bit, that's it. You know how large is the ID field? And did I actually mention that? Let's go to the object ID. I actually mentioned it, someone highlighted it. 12 bytes. Dude, this is bytes, not bits. This thing is a 12 bytes by default. And it has like the first 4 bytes is the timestamp, the second 3 bytes is I don't know what. This is because Mongo decided to scale first, right? So they wanted their IDs to be unique across machines. So even the second 4 bytes is a combination between the process ID and the machine name, and so the ID is truly universally identified across machines. So that's why it's so big. 12 bytes is so large. Yeah, so it's 12 bytes compared to 8 bytes, right? Because 64-bit is 8 bytes and 12 bytes is 12 bytes, right? So 4 bytes extra. You might say, who cares? 4 bytes extra. But here's the thing. I didn't know. MongoDB actually allow you, and those who use MongoDB more might know, you can actually set anything in the ID field. So it's a user-controlled field. If you don't set an ID, it's going to generate one for you. But if you do set it, you can have it to be a very large. People can have crazy ID values. And guess what? The secondary indexes now has to point to the ID because that's where the data is. And that's where all the problems of MySQL arise, where if the ID is a poorly chosen value, if the primary key is a poorly chosen, like a GUID, right? Again, there's a lot of course, discussion about having a UUID as a primary key, but we know it's very large. If you use it as a primary key, then those primary keys are stored in the secondary indexes as values. And that's what bloats everything up. So now the secondary indexes just blow up, right? And that's basically the evolution of MongoDB, you guys, right? As a summary, we started with mmap, right? Moved to WireTiger, gain a little bit of new features, but introduced new problems. For Sync 5.3 and 6.0, you can actually do clustered indexes. Gonna see you in the next one. You hope you enjoyed this video. Goodbye.